Okay, and our next presentation is going to be from Team 6832 Iron Brain from Dallas, Texas. And they have been a robotics team since 2012. Their main goals consist of pushing the limits of high school robotics and breaking out of the box with innovations and designs while improving STEAM accessibility in their community. Iron Brain's presentation today will tell the story of their evolution of their Swervolicious Swerve, which has been in the works for almost 2 years now.
Okay, so everybody, we're at FLYSET 6832, and just before we move on, can I get a quick raise of hands of anybody that used the QE drivetrain this year? Okay, cool. If you did, just close your eyes and ears for this one.
I know we've all been having a harmonic fever, but it's important to know the differences. So Mechano is really great at moving forward with high speed and momentum, but it struggles whenever it's strafing, causing lower speed, power, and traction. It also requires more wheels. Kiwis are really cute, but let's be honest, their traction and speed are a little something. So let's move on to Swerve. Swerve is able to deliver full speed and full power. Swerve is able to deliver full speed and full power all the time without compromising traction and being compatible with multiple counts of loops.
Swerve for the win!
You're ready.
This our story on discovering and overcoming challenges. What Swerve is many bonds, like mechanical complexities, expensive non-sensitive costs. Also, power transmission challenges, and for FEC constraints on motors, they can utilize servos for steering. Also, one of our biggest problems we faced was direction lag, which is caused by the rapid changing direction. This is worse at 90-degree angles because each module has an individually switched steering by 90 degrees, and servos are slower than motors.
So when designing a Swerve module, we had certain priorities that we kept in mind. One of the things that we wanted to use those ultra penetrating motors just for the purposes that it would make it easier to dial in those gear ratios when you want to change robot design or for the upcoming feature season. Keeping the feature season in mind, we designed for high ground clearance, and to do this, we put the motors and servos on top of the module, which is pretty unconventional and some the steering, and that's because FTC has motor limit, and so we weren't able to put it there.
Today we will be discussing the evolution of our Swerve module from our completely unplanned design shown on the left, all the way to our well thought out and developed and working Swerve module on the right.
So, in case you didn't catch the presentation last year or don't recall much, here's a short recap. First of all, we went through 4 main iterations before we were at a usable stage. V1 had incredibly inefficient power transmission because of the large pulleys. In V2, we removed both of them and replaced one with the motor that would directly drive the gear train inside the module. However, we had no way of actually controlling the orientation of the wheel. In V3, we added a steering captain, which was a built 3D printed part with a built-in pulley that allowed us to control that wheel orientation. V4, this was our first usable prototype of our design. Now, we switched over to the Rev proprietary motors with that configurable gear ratio for more experimentation, added a potential servo module, and a through-bore encoder so we could track that position of the wheel and the servo. Now, we were using Rev servos. Yeah, Rev servos. So we had this made the design process and the process a lot more complicated. However, it's all we had at hand and allowed us to further push just to experiment to find new solutions. Now, these are a bunch of the cards from our experimentations from V1 to V4 and a little bit of our next version. So everybody say hi to Pretty Boy. Pretty Boy was designed after last year's FLYSET in order to revise our Swerve with our standard iron ring materials. So any structural plates were thinned down and made out of 3mm carbon fiber. Carbon fiber is incredibly light, is lightweight and strong. However, it's overkill for FTC and needs to be handled with caution. However, we prefer to manufacture that in-house compared to aluminum. Then our tire is made out of 85A flex TPU, which we use for similar applications, including freight frenzy and power. The rest of our 3D printed parts were remade in nylon, which, yes, also pretty overkill for FEC, since all you really need is PLA and PPG. We like is extra strength, flexibility, bound capabilities, and heat resistance. Now that last one is especially important for Texas, since FLYSET can perform quite easily in a hot car or in direct summer, which has actually happened to some of those parts. Let me show it really.
It's like half great.
No, it's good. So we run. So after testing pre-board, we saw that there were some design issues that we weren't happy with that really stressed. So here's run. Run is essentially a complete overhaul of design choices made with pre-board. We've decided to remove any purely aesthetic holes, large chamfers, and overall refigure the parts. We've replaced one of the parts with another carbon fiber part, changed that dead axle on the wheel to an 8mm Rex, cut down on bulkiness of that servo module, as well as adding tensioners for that servo module and for that wheel assembly at the bottom.
Powers transfer down the motor shaft through the gear train down the secondary axle that drives the pinion gear. It meshes with the hub valve gear that ultimately gives power to the wheels.
Let's see the video.
Do you want me to play the whole
Yeah,
thing?
you can move on.
Oh.
So steering is controlled, wheel steering is controlled by a servo via two pulleys and a belt. The reason for that non-1-to-1 gear ratio was to leave the possibility of using a positional rotation servo open, so we have that extra telemetry. Now, to deal with servos that don't have a built-in analog encoder, or to deal with our gear ratio shenanigans, we've added that three-board encoder at the bottom in order to track the position of that servo, and then use the math and track the position of the wheel. Now, we've also mounted our servo module on slider holes so that we can tension it, so we don't have to rely on perfect C2C elasting throughout multiple competitions.
Now that we got this over with, we can get into how we turn this abomination of a test platform to a wheeling capable carbon fiber monstrosity. In continuation with our Denki test platforms is Swerve version 2. Although this was not a professional chassis, it allowed us to build or develop our Swerve module from the ground up. Our test concluded that a one-way chassis was absolutely possible to design. However, you had no way of controlling the robot orientation if you implemented this. All the Omni wheels are just acting as casters, none of them are actually being powered. As for code, we started off with a completely driven and incrementally driven software, and then we moved on to a robot-oriented drive.
So now you can see our dual swerve, which is our next step. So it has two swerve modules mounted opposite of each other with a 3D printed chassis. We 3D printed this because we weren't really concerned about durability for this specific iteration. You can see that we reduced the number of those Omni wheels to just 2 sets, and again, they're just there to provide balance without restricting the hollow on the movement. Our goals with this chassis were to develop good orientation control combined with omnidirectional travel. And while we were able to develop those two things, we didn't get around to driving while turning.
On the left, we can see a video of our dual swerves, omnidirectional driving, and simple in-place turning. The dual swerve is a test run of the grunt prototype. Now, the direction of the deflection of the joystick determines whether the chassis moves counterclockwise versus clockwise, and the amount of power that you put into the joystick determines the wheel's power. On the right, we can see the robot-oriented in-place turning, where the direction of the front of the chassis turns towards the direction in which the joystick is deflected.
This is our TriServe chassis. It is our first attempt at creating a competition-ready chassis using simply Swerve modules. While it is unconventional due to fabrication and materials, it is lightweight, strong, and highly maneuverable. It also has optional autopods, and it has vision capable. It has not been used in a competition yet, and it is nowhere near completion.
So this is our TriServe actually in action. Thanks to our previous test runs and how we missed, we were able to get it up and running shortly after this finished being built. On the left is TriServe's first steps, or I guess goals, however you like to call it. This was allowed us to see how the different wheels mix together in order to drive, and any possible issues that were still remaining in the actual pods. Now, on the right is Swerve's off-roading capabilities, whatever you'd like to call it. I'm not really sure. but just wait a minute. There you go. So we've seen that Swerve is actually does a pretty good job at going over obstacles, ramps, and even concrete, like you saw in some of the previous videos.
Here's a stress testing a new chassis at Caltron. In reality, you and I know we're just having a little too much fun with that new chassis. But this did show how resilient it can be and that it can actually hold up to a beating in a match.
These are our swivel dynos. So we use them to allow the Swerve modules to be able to turn and drive without actually moving. This helps us during debugging and calibration.
So we've gone through a multitude of different kind of indexing strategies as well as tracking the position of our wheel. First of all, like we've been mentioning, that through-board coder is used to it uses math and the position of the servo to track where the wheel is facing. Now, for our indexing, we did that in case that encoder slips or wheel slips, and so that we can have some kind of calibration sequence. First of all, we went with limit switches. However, we found that our design ended up with them breaking or having spotty physical contact. So we moved on to using that spiral pattern along with infrared analog sensor. So what it does is it reflects light off of that spiral, and once it gets to the very tip, it'll show no light is being reflected, and therefore we are in X position and can now recalibrate to that position. However, if this ends up not working or being too inefficient, we're thinking of switching over to magnetic limit switches or something similar.
Standard Swerve code assumes 4 modules on quadrilateral corners, but due to the mono, dual, and tri-Swerve evolution, we needed different code requirements. Therefore, we are considering creating an N-Swerve controller, which is compatible with Roadrunner and is capable of having any number of Swerve modules on the chassis. This allows the center of rotation to be placed either on or off the chassis and without restrictions.
So there's some stuff that we still like to accomplish with this chassis. Some of them being finalized the auto calibration, the N-Swerve code, and a module build guide. We want to upgrade those servos and experiment more with the tire design. We'd also like to do some performance profiling and create our own custom breakout boards. We want to finish off that chassis because we still haven't mounted a geometry or that swivel camera. And then if we gauge enough interest, we're thinking about a possible open source of the design and code.
Before we get to questions, this is our Instagram QR code. Please follow us. And also our website to see in-depth blogs about what we do as a team.
Thank you.
Okay, thank you guys. That's very, very innovative design.